Have you ever wondered how your ride-sharing app just finds you a driver in minutes? Or how a giant university assigns thousands of students to their classes without a single conflict? Well, the answer isn't magic. It's actually a really powerful idea from a field called graph theory. And today, we're going to dive right into this fundamental problem of fair allocation.
At its heart, our world is just filled with these kinds of pairings. Think about it. Whenever two different groups need to be connected based on who's compatible with what, we are facing a matching problem. And this is a challenge that's happening all around us, millions of times a day. And yeah, that's the real question, isn't it? It's not just about making pairs. It's about making the best possible set of pairs, making sure that no resource is double-booked, and that as many needs are met as we can. So, how do we pull off this perfect, conflict-free harmony?
Well, the answer starts with a really simple but incredibly powerful way of just visualizing the problem. We need a special kind of map, and that map is called a bipartite graph.
So, what is it? Okay, imagine you've got two separate groups of dots, or nodes. Let's call them Group A and Group B. A bipartite graph is one where you can only draw lines, we call them edges, from a dot in Group A to a dot in Group B. You can never, ever draw a line between two dots in the same group.
And this structure? It's literally everywhere. One group could be jobs, the other could be qualified workers, or maybe it's computing tasks on one side and available machines on the other. The key rule is what gives it all its power. Connections only go between the groups. A worker can connect to a job, but they can never connect to another worker. This simple rule is what perfectly models the problem. Okay, so now that we have our map, matching is just us choosing a set of those connecting lines. But here's the absolute critical rule. Each dot, each node, can only be part of one chosen line. This is how we guarantee zero conflicts. A worker can only take one job at a time, and a job can only be filled by one worker. Simple as that.
And there are different flavors of this. Any valid set of pairs is a matching. But what we're usually hunting for is the maximum matching, the absolute biggest number of pairs we can possibly make. Now, the Holy Grail, that's a perfect matching, where every single node on both sides finds a partner. But in every case, the goal is exactly the same: total conflict avoidance.
So, how do we find this maximum matching? You might be thinking, well, just start pairing things up as you see them. It seems simple enough, right? But this super intuitive approach has a major hidden flaw. This whole first-come, first-served idea is often called a greedy algorithm. It makes the choice that looks best in this very moment, just grabbing the first available pair it finds without even thinking about the consequences down the road.
And here is the trap. On the left, the greedy choice makes one super easy diagonal match. Boom, done. But in doing that, it completely blocks any other matches from being made. The optimal solution on the right, though, it's a bit cleverer. It finds a way to create two matches. It proves that the first, most obvious choice isn't always the best one for the system as a whole.
So, if the greedy approach is a no-go, what's the better way? Well, it involves this clever and almost counterintuitive technique for improving a matching we already have. It is all about the art of the swap.
The key tool here is something called an augmenting path. Now, I know, it sounds technical, but the idea is actually pretty simple. Imagine tracing a path that starts at a free, unmatched node on one side and ends at a free node on the other. The trick is that the path has to alternate. It has to follow a line we haven't used, then one we have used, then one we haven't, and so on.
And here is where the magic happens. Once you find one of these special alternating paths, the next step is dead simple. You just flip the status of every single connection along it. Any edge that wasn't in our matching gets added, and any edge that was in our matching gets removed. And because the path starts and ends with an unused edge, the incredible result is that the total number of matched pairs goes up by exactly 1. We've just improved our entire solution.
The crucial insight here is that to get a better overall outcome, sometimes you have to break up a perfectly good existing pair. It's like an existing match might seem fine on its own, but an augmenting path might show us that by breaking that one connection, we can actually create two new matches somewhere else, leading to a much better solution for everyone. Now, this whole process of finding better and better paths, it might sound a little familiar to some of you. And there's a really deep connection here to another famous problem called maximum flow. It turns out that finding the biggest possible matching is really the same problem as finding the maximum flow through a special kind of network. It's one of the most elegant connections in computer science.
You can actually transform any matching problem into a flow problem with just a few simple tweaks. First, you add a single source node that connects to every node in the left group. Then, you add a sink node that everything in the right group connects to. Think of it like a single faucet and a single drain. If you say every pipe in this new system can only handle a capacity of 1, then the total maximum flow you can push from the source to the sink is exactly equal to the size of the maximum matching.
Okay, so this is all fascinating theory, but what does it actually mean for the real world? Well, the impact of bipartite matching is absolutely massive. It is the silent engine running behind countless systems we rely on every single day. I mean, just think about it. Assigning doctors to hospital shifts, students to university courses, drivers to riders, or even ads to viewers on a web page. What about balancing workloads across servers in a massive data center, or scheduling tasks on a factory floor? All of these are real-world matching problems, and they're solved efficiently and fairly using these very algorithms. Modern logistics and our digital world are literally built on this idea. And this really brings us to the most important takeaway. When you get right down to it, bipartite matching isn't about finding the fastest route or the shortest path. Its core purpose is something much more profound. It optimizes for fairness. It is a mathematical guarantee that, given a set of constraints, we can create the maximum number of successful pairings, leaving as few as possible behind. It's a blueprint for conflict-free allocation.